This is the intro video for AP Calculus BC, section 7.2. You're going to be focusing on the washer method in this video. So the washer method is really not that much different than the disk method. All the characteristics really are the same, except the solid that we get is going to have some kind of a hole or a gap in the middle. And so we'll look at the formula for the washer method here, look at a little diagram, and then we'll get into an example. So the formula for the washer method, of course, these two formulas are the same. One of them is in terms of x, the other one is in terms of y. So we're not going to look at those as being totally different. There's going to be your axis of rotation is going to be, different orientation for the two different formulas. So we will use for this one, the one on the left, this would be for a horizontal axis of rotation. And the one over here would be for a vertical axis of rotation. So it's going to be the same concept as before. We want our representative rectangle, representative washer to be perpendicular to that axis of rotation. So that's why we're going to have x's or, in the other case, y's. Okay, so notice that this does look sort of like the disk method. The disk method, if you remember, is pi integral r squared. So this is pi integral r squared minus r squared. One of them is capital R, of course, the other one's little r. Here's what they mean. Capital R is the distance from the axis of rotation to the further function, or it's the bigger radius, if you will. And then little r would be the distance from the axis to the closer function, or the smaller radius. Of course, capital R of y and little r of y mean the same thing. They're just in terms of y instead of in terms of x. I want to draw a little picture of this, and then we'll get into an example. So let's say we have two functions here forming a region. Let's say we got something like that, and then we've got a different function that does that. I don't know, something like that, giving us a region right here. And let's say that that region would revolve around the x-axis. First of all, hopefully we can see that there's quite a bit of space. The important thing is there's some space between the axis of rotation and the region. And so as you rotate that region, the other part of it would look something like this. You've got a big gap in the middle, right? You've got a hole there for sure. And so because there's going to be a hole right there, we've got to use the washer method. So in any case, here's what the r's would look like. The capital R is the distance from the axis of rotation to the further away function. That would be this distance right here. And then the little r would be the distance from the axis of rotation to the closer function. So that would be this right here. And we would use those within the formula volume equals pi integral from a to b of big R squared minus little r squared. And in this case, it would be a dx rectangle because we've got a horizontal axis of rotation. Okay, so we'll do an example of this here on the next slide. Work with me here and check this out. Okay, so we're going to be using region P for several questions here. So I'm going to go ahead and draw region P. Region P is bounded by y equals root x and y equals x squared. So with our x and y axis, y equals root x looks like this. And y equals x squared, of course, looks something like that. And the region formed by those two graphs is right here. Okay, so we are asked to then take that region and revolve it around the x-axis. That's kind of like the one we just looked at. So I'm going to put that little rotational symbol in there. Well, first of all, we want to make sure that we can visualize this well enough to recognize that the resulting solid is going to have a big gap in the middle. It's not going to have a hole, right there at the origin. That would be, the hole would be plugged right there, but for the whole rest of the shape, you're going to have a gap in the middle. So we're going to be using washers here. So we're going to set up our formula, and here's what I typically do. Once I recognize I'm going to use washers, I set this up. Volume equals pi integral of big R squared minus little R squared. And I got to put a dx or a dy in there, but I want to get that set up. I don't want to mess that basic framework up. Okay, so let's decide, is it going to be a dy or a dx? We're rotating around the x-axis, so we want our representative washer to be perpendicular, there we go, to the axis of rotation. So it's going to be a tall, skinny representative rectangle, making it dx thick. So I'm going to put a dx on the end of this. The next thing I'm going to do is I'm going to try to figure out the limits of integration. So I'm going to be accumulating from left to right across the region here. So I'm going to start here and I'm going to stop right there. So I don't know, I feel pretty comfortable saying that the intersection point there on the left is 0. The intersection point there on the right ends up being 1. You could use a system of equations to figure that out. I think guess and check would be a pretty easy method here as well. Okay, so then the final thing we're going to do here is we are going to plug in the radii, the big radius and the little radius. So the big radius is the distance from the axis of rotation to the further away function. So that would be represented by this green line segment. Let's try that again. There we go. So that distance literally is a y distance, right? It's from the x-axis up to some spot on the graph. So I could put a y right here, but I remember that it's going to be a dx integrand, and so I know that I can't use that in the end. It's a good intermediate step, but I want to replace that, or I want to substitute in for that with something that is only in terms of x. And so if I think about that purple graph, I know that y equals root x. And so what I can do then is I can replace that y with root x. And so I'll just put a root x right there for that first radius. Second radius, of course, is going to be somewhat similar in this case. The smaller radius would go from the axis of rotation to the closer function, represented by that little blue line segment. So once again, that literally, if we want to be super literal about this, that is a y. It's a distance from the x-axis up to some point. But we know we can't finish with that, and so I think about, all right, well, what is connected with that graph? Well, that's the parabola, y equals x squared. So that means I can replace the y in there with x squared. So that's what I'll do. So x squared would go right there. Okay, so at this point, this is perfectly set up. Hard to know whether you're going to have a calculator or not with this. This is very doable without a calculator. So I'll work through this real quick, and we'll see what we come up with for an answer. So volume equals pi integral from 0 to 1. Root x squared is just x. X squared squared is x to the 4th. Hopefully I don't run out of space here. We'll see. So as I find my antiderivatives, it's going to be pi, and it's going to be 1/2 x squared minus 1/5 x to the 5th, evaluated from 0 to 1. So I'll plug in a 1, and I get, I'll just do this kind of quick here, 1/2 minus 1/5. And when you plug in a 0, both terms end up going to 0. That won't always be the case, but in this case it is. So this will actually work out pretty nicely. So volume equals pi times 1/2 minus 1/5. So it would be 5/10 minus 2/10, so 3/10. So I think we'd end up with 3/10 pi. Okay, so we got a bunch of other examples to do. We'll do those in class when I see you next time.